I'm Nichole Kass, and I'm a systems engineer from Synchronous. My presentation is Getting Started with Model-Based Systems Engineering and Product Development. I presented this in July of 2016 at the INCOSE International Symposium in Edinburgh, Scotland. Model-based systems engineering. If you believe all the hype, model-based systems engineering is going to save the world. When I started looking into this, there were over 2,000 papers on the topic from past INCOSE symposiums. That's a lot of information. And model-based systems engineering has a lot to offer. It'll help you manage the interconnectedness of your project elements. It'll help you improve your communication, increase productivity and quality, and reduce the risk. These are all things we're looking to do on our projects. But when we got into model-based systems engineering, the framework that came out of the box with our tool had just too many items. There were more items and more types of connections. And even more items and more connections. And if even one connection was incorrect, the whole model fell apart. There were a whole bunch of diagrams. We didn't know which ones to use. There was so much information in both the model and any output documents that it was just so enormous and so much information. It was nearly impossible for us to get people to review and use the outputs that we were creating. Our systems engineers are tech leads as well as in charge of requirements, and we were spending so much time with requirements and our models that we weren't leading the technical direction of the team. We decided to take a step back and look at what model-based systems engineering really is and what it is that we actually need. We thought there's 4 kinds of model-based systems engineering. At the bottom end is none. If you're doing document-centric systems engineering, you're not using model-based. One step up from that would be a requirements management tool like DOORS, which helps you manage your requirements and your verification. If you want to add diagrams on top of that, that's the next step up. And then some allow you to do analysis as well, which is an even bigger step up from that. So a little context about what we were thinking about when we went to go choose what level of model-based systems engineering we needed. At Synchronous, we do new product development. We usually get into products prior to requirements and then hand off for manufacturing and validation. We do aerospace, medical, industrial, and consumer, so we needed something that would work in all of those different industries. Our projects range in size from 100K to 2 million, which is a pretty big range, and they last anywhere from a few months to a year. So we had a lot of different project types and sizes that we needed to accommodate. The standard schema was too powerful for our needs. We decided we needed to simplify it. This simplified schema that we came up with is great for model-based systems engineering beginners who are looking to get into MBSE, or for maybe some of you MBSE pros out there that have some smaller medium projects. Now when I talk about a schema, this is the structure or the framework that sits underneath your database in your model. It includes what items are you going to capture in your model, how they trace to other items, what attributes are stored with each item, and what document artifacts you're going to create. The customized schema we've come up with is relatively software agnostic, providing that the software you're using allows you to customize the schema, which many do. When we set about simplifying the schema, we decided to completely throw out the old method and build our new one from the ground up. And this is what we came up with. This diagram shows all of the items that we selected to include in our schema. Items are the containers in the model that hold the information for a single thing. A requirement is an item, and a verification is an item. I'm going to walk you through why we chose each of these items and exactly how we use them throughout the project. When we were deciding which items to use, we started with the standard systems engineering V diagram that we've tailored for product development. You've probably seen something similar. We first ID'd the 3 items that we needed for requirements and test. These are the originating requirements, system requirements, and verification. These are the things that a requirements management tool will give you. We added these to provide traceability so that we can ensure that all the requirements trace to verification. since this is a very important aspect of a systems engineer's job, and MBSE allows you to do this very easily. Next, we decided to add 3 diagrams. We wanted to have one diagram for each phase leading to development, and we chose the one that is best suited to completing and communicating the goals in each of these 3 phases. In the Stakeholder Needs phase, we chose the use case diagram. This helps us systematically find all the high-level needs during this phase. During design inputs, we chose the behavior diagram so that we can describe and capture the behavior requirements of the system. And during architecture, we chose the architecture diagram so that we can capture and identify all of the interfaces, which are also very important to a project. In addition to these, we've also started using issues and documents. These are used throughout the entire project, and they're linked to all the other item types. So we're going to start by talking through these 2 because they're very powerful since they're used throughout the entire process. The first is input documents. This is a documented source for all of the items in your model. It allows you insight into why and when certain items were changed or created. This is really useful during your high-stress project points, like failed verification or if your schedule is running over. If you failed a verification and you need to know whether you need to change your design to meet that requirement, or if maybe you can change the requirement so that your design works, if you can trace back to exactly where that requirement came from and what all the decisions were that led up to it, will help you be able to make informed choices about what you need to do about that failed verification. Same with schedule overruns. If you need to go back and look at perhaps you had a lot of requirements changes that are causing your schedule overrun, or one particularly difficult requirement that was introduced late, you have all that information you can go find to help you. We also use the issues item type. This is where we capture our issues or open questions within the model, and it also helps us maintain a history of those key decisions. Each issue is linked to the affected item so that it shows the impact of a decision, so you can tell how far reaching into the project it is. Once a project reaches a certain stage, an issue should be tagged to every item that isn't firm and decided upon. For us, that's usually around the architecture phase. Let's talk a little bit about what an item looks like within your model. There's a core set of attributes that we like to use on nearly all of our items. We use an ID number. This is incremental to never changing number. It allows us to maintain the history. We give everything a name, just something short and unique. Everything gets a status. This tells us how well defined this item is and how mature our model is. We can look at some statistics in the model to see how many items are firm and how many are initial. And then everything has a description. This is the main text of your item. In your requirement, this would be your shell statement. We also like to give things different allocations. We typically use 3, allocation, discipline, and group, and we can change these up on different projects depending on what the needs are. We also like to add additional attributes as necessary, and we'll get into those more specifically with a few different item types. Also, we need to decide what output documents we're going to create for our model, since unfortunately we still live in a document-centric world. Documents need to be output for things like regulatory submissions or for people without access or knowledge for how to use your MBSE tool. The documents that we've chosen to include are an originating requirements trace and a use cases document during Stakeholder Needs, our product requirement specification, which also includes our verification plan during design inputs, and system architecture document in the architecture phase. I'll go into more detail on each of these later on. Fortunately, having all of your information captured in your model, these documents can be output directly, and you can keep them in sync with each other, and you don't need to duplicate the work. So if you set up your output templates correctly, you can just output your document and you're good to go. So I'm going to walk through the product development process phase by phase and talk about what activities are done and how that relates to the model. So the first phase is Stakeholder Needs, where we do our originating requirements and our use case diagram. There's 2 main goals in this phase. The first is we want to reconcile all the project inputs. I don't know about you guys, but when we start a project, we get a massive list of stuff. We get legacy requirements, we get feature lists, marketing requirements, emails, all kinds of stuff that needs to be captured And then we need to dig through it and trace and reconcile those into usable things. So we capture all of those into our originating requirements. We trace and reconcile them into use cases, interfaces, and system requirements. And then we output all of that into the originating requirements trace. A little more detail on how we do this. A lot of tools have a document import feature, so you can take those documents and import it straight into your model without having to recreate all the information. We take each document that we get and we save the source as our document item type. And then each item within that document becomes its own originating requirement. So in this example, each of those bullet points in this RFQ becomes its own separate originating requirement. We then have a concise list of all of our inputs, so we can trace through them one by one and decide whether they should go into use cases for our behaviors, interfaces for the interfaces, and system requirements for all of our constraints. We output all of that back into an originating requirements document so we can communicate back to our stakeholders. This is how I interpreted something, and this is what we're going to use going forward. This is something that can show your stakeholders when there's conflicting input requirements. For example, in this requirement, one stakeholder wanted a cell phone charger and wanted a coaxial barrel connector. This tells what we chose going forward and lays that out. The second goal in this phase is to uncover the missing high-level needs. We use a use case diagram to consider overlooked use cases. We use the use cases to add critical details, and then we output all of this into a use cases document. The use case diagram is a systematic approach that helps us make sure we catch everything. We look at what is inside and outside of the system, who and what is interacting with the system, and what all of those interactions are. We then take a look and add some more details to those. Here's an example of where you can see additional attributes that we've added to a use case. This item type now has preconditions, the main event flow, postconditions, and alternate flows. Each of these is an additional attribute that we've added. We use these to capture the detail of the use cases. We then output all of those use cases and the use case diagram into the use cases document. The next phase is design inputs. Since requirements aren't complete until we know how to test them, we also consider verification in this phase. The main goal of this phase is to provide inputs so that we can architect the system in the next phase. We look at all of our requirements, we plan our verification, and then we output all of this to the product requirement specification. The first item type that we're going to consider in this phase is the system requirements. There's two different types of system requirements that we consider. First is a constraint requirement. This is what a system is or has, such as the location of a charge port, and a performance requirement. This is what the system does, such as how fast it needs to charge. The importance between this distinction will be clear in a minute. The diagram we use in this phase is a behavior diagram. This shows the time dependency and decision dependence of the functions of the system. There's many different types of behavior diagrams, and it doesn't really matter which one you choose. There's also many theories for how to represent your information within a diagram. But the thing to keep in mind is that you don't have to be perfect. We're not doing analysis here. The only important thing is that you're consistent. Choose something and go with it. It doesn't matter if you're using your and choices correctly or your or choices correctly. As long as you're consistent and you communicate and you use these diagrams as a communication tool, that's really what we're after here. So don't get too bogged down in the details of making it perfect. Within a behavior diagram, each of the functions within the diagram opens up into its own item type of a function. Now, each of these functions is a requirement and should be written as such. Some rules of thumb to keep in mind when you're doing diagrams. Remember, we're using these for communication, so you want to keep them simple. Keep it to about 5 to 9 items per diagram. We want to try and keep one diagram on one page. These help you keep it simple and concise. And also remember, don't do the engineer's job for them. These are your core requirements, not your design, so you don't want to get too detailed. If you get too detailed, you're going to be spending a lot of time fixing your model as the design evolves, and also you're going to be over-constraining your engineering team, so they're not going to be very happy with you either. Back to those performance requirements a little bit. Each of those performance requirements is going to get linked to a function. This gives them the context. So in this example, there is a function to charge the device, and that performance requirement for how fast it needs to charge would get linked there, so that you have the whole context from the diagram to the function to the performance requirement all in one place. Next, you need to plan your verification. You want to get alignment on the method and owner. All of your system requirements and the functions in your behavior diagrams should all be traced to your verification item types. Most model tools allow you to very easily test your traceability to make sure you get 100% test coverage for all of these things. We then output all of this into our performance requirements specification. We like to split this up into 3 different documents. It helps make it a little less overwhelming for those not used to looking at this kind of information. The first one is a functional spec, where we put the behavior diagram and the performance requirements. The second is the constraint specification. This one's particularly useful for the mechanical and hardware engineers. Then we have the verification plan, where we outline how we're planning on testing things, and then we show which linked requirements that verification item is testing. There's many different ways to show it. This is just the way that we like to show it here. The final phase before development is architecture. This is where we do the physical architecture diagram. The main goal here is to select an architecture that meets the requirements. So we want to look at our architecture. We want to capture all of our interfaces. Since interfaces are requirements, we want to trace those to verification, and then we output the architecture and interfaces to the system architecture document. When looking at the architecture diagram, we want to look at who and what is interacting with the system, what comprises the system, and how everything is connected. Those who and what interacts with the system, these should be the same as the who and what are from your use cases. If you're missing one in either diagram, you probably overlooked something. This is a systematic approach to help you identify what all of the interfaces are. Because as we all know, one of the first things to fall apart in assembly and test is the interface. So if we capture them early, that'll help us prevent some of those problems later. When we're capturing our interfaces, we look at them in 3 different categories. The first is an external interfaces. This is something to outside the system. Then we have our internal interfaces. This is between components within the system. And we like to split these into internal and critical internal interfaces. The critical internal interfaces are things that are high risk, such as between subsystems being designed by different groups or on a particular safety system, something that we want to consider a little more closely and make absolutely sure is done correctly. Both the critical internal and the external interfaces are defined and verified, whereas the internal interfaces are left to the discretion of the engineer to design and document. Since those interfaces are requirements, we trace them all to verification, and then we output all of that to the physical architecture document. We have our interfaces, which are defined. We can also define our components. If you've done any trade studies to select particular components or have any particular constraints on the components, this is a good place to capture those. And then we re-release the verification plan because we've added additional items traced to the verification. The physical architecture diagram also gets included. That brings us to development and beyond. At this point, our base model is complete. Our job now is to refine those incomplete items. All items without a firm status should have an issue tied to them so you can track them to completion. And use your documents and issues items types to help you track as decisions are closed and which ones still need to be closed. So that's it. We started with something overwhelming on the left, and we arrived at something that's much more manageable and has just enough information to be useful. Helps us clear our systems engineers to go be the technical leads on our projects instead of spending all the time in front of a computer bogged down trying to make the model work. So that's it. Go get started. Set up your schema. If you're new to model-based systems engineering, I recommend following the setup as closely as possible. My paper has some more details about more specifics to getting it set up correctly. And if you're already using model-based systems engineering, maybe consider this approach for scaling back for more agility and less overhead on some of your smaller projects. Use your model. If you don't write it down, it didn't happen. The model is where you want to store all of that information. Communicate with your teams. Remember, this is a communications tool, not an excuse to go hide in a corner somewhere. You want to show value to your teams. Use the traceability to help quantify scope changes, and use the issues to track and close high-risk questions before your teams start getting antsy that they don't know what they need to do. And you can then build on it and add any additional items as necessary. For example, we like to include our risk assessments on medical projects into our models. That's it. Thank you.